Imagine you're given a number pattern and asked to find the 50th or 100th number in that line. You could sit down and calculate every single step by hand, one by one, until your chalkboard runs out of space. Or you could build a shortcut. Today, we are going to look at this specific sequence: 4, 11, 22, 37, and 56, and figure out how to build the general term for it. This is the master formula that describes the entire pattern. Now, looking at that formula, with its squared terms and multiple variables, might seem intimidating. But if you know how to subtract, and you can recognize a basic linear pattern where numbers go up by the same amount each time, you already have every skill you need to solve this. By the end of this, you won't be guessing what comes next. You'll have built the general formula that lets you calculate any term in the sequence immediately. Let's analyze the gaps in our sequence. From 4 to 11, it increases by 7. From 11 to 22, it goes up by 11, then 15, then 19. These are our first differences. This is where a lot of people stop. They see that the amounts added are changing and assume there is no clear pattern. Because the first differences are not constant, we know this isn't a simple linear sequence, but we need to keep digging. Let's look at how those first differences change. From 7 to 11 is a jump of 4. From 11 to 15 is 4. From 15 to 19 is 4. These are our second differences. Finding a constant number in that second row is the definitive mathematical proof that we are dealing with a quadratic sequence. Every quadratic sequence will have a constant second difference. That orange number 4 defines the first coefficient of our formula, but pay close attention here. The most common mistake is plugging that 4 directly into the formula as the letter A. Do not do that. Instead, we apply a mathematical fact. The second difference is always twice the value of A. To find A, we divide by 2. If 2A is 4, then A must be 2. Now we update our master template. Our formula officially starts with 2n squared. Step 1 is done. To find the rest, we use a technique isolating the remaining variables. If we subtract the 2n squared growth from our original sequence, we strip away the complexity. What's left behind will be a basic linear pattern. This grid is our starting point. Row 1 is our original sequence. In row 2, we calculate 2n squared for each position. Position 1 gives 2, position 2 gives 8, then 18, and 32. Next, we subtract row 2 from row 1 vertically. Be careful with negative numbers here. 4 minus 2 is 2, 11 minus 8 is 3, 22 minus 18 is 4, and 37 minus 32 is 5. Look at our remainder sequence: 2, 3, 4, 5. This linear pattern increases by exactly 1 each step, so our variable is just n. Since it starts at 2, the formula is simply n plus 1. Finally, we take our quadratic piece, 2n squared, and combine it with our linear piece, n plus 1. We now have our completed master formula. By removing the heavy quadratic part of the sequence, we exposed a basic pattern hiding underneath that we already knew how to solve. Let's test this to make sure it works. If we want the third term, we plug in 3. 2 times 3 squared is 18, plus 3 plus 1. That equals 22. It perfectly matches our original sequence. Now for the real payoff. Remember that 50th term we dreaded finding manually earlier? Let's skip straight to it. Plug in 50. 2 times 50 squared is 5,000. Add 50, add 1, and we get 5,051. Instantly. Let's review the 4 steps to build this. 1. Find the constant second difference. 2. Have it to find the value of A. 3. Subtract your an squared sequence from the original. And 4. Find the rule for the linear pattern that's left over. Here is your challenge. Take this new raw sequence: 3, 6, 11, 18, 27. Apply those 4 steps, find the general term, and post your final formula in the comments below.
You've just turned what used to be a long manual process into a reliable mathematical system. You now have the exact tools you need to predict what comes next.